Hello everybody, I'm going to do number 5 from the homework for chapter 11, section 5. The question that we're presented with is to find the area inside the lemniscate of r squared equal to 42 cosine of 2 theta, and the outside circle, which is r is equal to the square root of 21. So as you can see here, I've sort of found this cool little graphing app for my tablet. And I've created this graph here to kind of show you what this is going to look like. I think in math lab they had this circle more of an oval. I think that was just to exaggerate where maybe the intersections occurred. But as you know, r equal to the square root of 6 is going to be a circle. So obviously being a circle, it will be symmetrical, not oval shaped. But we are set to find the area inside of the two shapes given. So initially, I thought that it might be this area here, but in fact, it's really this area, because you've got the inside sort of circle here, or the outside, I guess, and then they're calling this the inside. If anybody wants to explain maybe why we chose the outer one versus, doing this area right here, that might be helpful. I just kind of went along with, quite honestly, what Math Lab had. But to me, it made sense that the area inside the two shapes would be given by maybe this, but perhaps that would then just be what the circle encompasses for area, not what the two shapes hold for area. Anyways, moving on, the first step that you want to do when you're solving these is to graph it. That way, once you graph it, you can kind of see what you're looking for and what you need to solve for. Here, we know that our theta is going to be, oops, that's really not a straight line, is it? Our first theta is going to be 0, because these two graphs intersect at 0. Well, not intersect, but the first angle is going to be 0, because that's the sort of bottom of the shape, if you will. And then the next theta is going to be this angle right here, which is where the two graphs intersect. So we'll call that theta. And then that would be once we solve for that, that'll be the upper limit of our integral for finding the area between these two shapes. So after we've graphed the two equations that we have, we want to go ahead and set them equal to each other to find out where they intersect. This will help us to find our limits for the integral. So what we're going to do is we're going to set 42 cosine of 2 theta equal to 21 and solve for that. And when you solve for cosine of 2 theta equal to 1/2, you get pi over 6. So once you do that, you're going to know that that's going to be the upper bound to the shaded region, and you'll be able to use that in your integral. So then we're going to go ahead and set up our equation for the shaded region. But first what we want to do is take a look at the equations that were given. In number 5, they sort of kind of throw you off by giving you one of your r's already squared. So really what you need to do is just square r equals to 21, which gets you r equal to 21, as you can see right here. So we've got r2 squared over here and r1 squared over here. So next what we can do is go ahead and set up that integral so we can sort of move on and find the area between these two objects. So what we're going to do is we're going to have area equal to the integral of 0 to pi over 6. Those are our limits of integration. We knew 0 and we solved for pi over 6. And then we're going to do 1/2 equal to r2 squared minus r1 squared, so we have 42 cosine of 2 theta minus 21. And then we're going to go ahead and we know that because if you go back, these two shapes sort of they're very symmetrical, as you can see. And we need these two areas, these 3 more areas here. But really, all that we're solving for with this first equation right here is going to be one of those areas. So what we could do is we could just solve that integral and times it by 4 at the end. But then you're going to have some, pretty fun fractions in there throughout the process of solving that integral. So what I did is I just took 1/2 times 4. Obviously that gives you 2. And then I'm just going to go ahead and apply that to the integral and go ahead and solve. So once I do that, and just keep in mind I took out the limits of integration here. I typically do that as I go through the problems. I've got area is equal to the integral of 84 cosine of 2 theta d theta minus the integral of 42 d theta. Well, this second one, that's easy as pie. But this first one here, we're going to have to solve. And I actually didn't solve it out here because I assume at this point that everybody can solve this integral. It's pretty easy. In the end, it gives us 42 sine of 2 theta minus 42 theta, and our limits of integration are from 0 to pi over 6. Well, we know if we put in 0 to these equations, the sine of 0 is 0, and 42 times 0 is going to be 0, so we don't have to worry about that limit, essentially, because it's going to just give us 0. So I just went ahead and I solved for the upper limit of integration, pi over 6, and that gave us this. So we have 42 sine of 2 times pi over 6 minus 42 pi over 6, and that gives us 42 sine of pi over 3 minus 7 pi, and the sine of pi over 3 is going to be the square root of 3 over 2, which eventually gives us this 21 square root of 3 minus 7 pi. That's going to be the entire area, not just one of the areas, but it's going to be all 4 of these areas on our graph. So again, like I said, you could go ahead and do the integral for just one of the areas, but because we had a 1/2, it made it just easier on me in the end to go ahead and simply just take the 1/2 times that 4 for the areas, or for the total areas, I guess, nevertheless, and then solve the integral from there. I hope that this video was helpful for you guys. I know that these problems are a little bit tedious in nature. They're kind of long. They take a little while. But I think in the end, they're kind of fun. And they kind of, I guess in my mind, bring everything sort of full circle. And polar coordinates, they might be intimidating, but they're not so bad in the end. I hope everybody has a great weekend, and I'll see you next week.